So hello all, so welcome to the optimization for ML and AI seminar. Today it is my great honor to introduce Tropp from Caltech. So Jill has done many great works in randomized numerical linear algebra and has found numerous applications in machine learning and data science. He has also made many abstract mathematical tools much more accessible to a wider audience, which I really appreciate. He's also an invited speaker for this year's ICM. So today he's going to talk about randomized linear algebra with subspace injections. Okay, Joe, the floor is yours.
Thank you so much for the invitation. So Legion and I are co-authors. He solved a problem that his advisor and I were unable to solve, and he wrote a nice paper which Legion got some recognition for. Thank you. So it's a pleasure to be here today. So many friends. So this is a somewhat technical talk on a topic in randomized linear algebra, which I hope has some interest to folks who work on computational linear algebra and optimization. I'll try and begin at the beginning so everything is accessible. But unless you have some experience with this, it may not be fully clear why these topics are of value. Okay, so the other important point before I begin, this is joint work with Chris Camano, who did all of the numerics, Ethan Epperle and Raphael Meyer, who did a lot of the theoretical work, and they're really the folks who drove this project to completion. Okay, so to begin, let's talk about sketching. So I'm going to give you a reminder about what sketching is. It's shorthand for randomized linear dimension reduction in this context. And it's one of the core tools in computational linear algebra and some types of computer algorithms now. Okay. So what is dimension reduction? So we've got some data, some vectors in Rn. You should think about n as being a large number. And as a consequence, it may be somewhat expensive to operate on that data. So you'd like to reduce its dimension to k, where k is a much smaller number, while somehow preserving its geometry. So here you've got an illustration of some high-dimensional data, and it's mapped down to, in this case, two-dimensional space. And you can see that the vectors still seem to have roughly the same interrelationships with each other. We should welcome the folks from the math department. Hi, Ryan.
Okay.
Rob.
50 minutes to walk.
I know. I'm sorry if I cut into your seminar, Ryan. Okay, so our goal is to reduce the dimension, preserve the geometry. So the most famous example of this principle is the Johnson-Linden-Strauss theorem, which states that we can preserve all of the pairwise L2 distances among these vectors in this high-dimensional space after embedding it into about log n dimensions, where capital N is the number of vectors. It has nothing to do with the dimension. It's a beautiful fact, maybe not very useful, but it motivated a lot of the subsequent work on the application of dimension. The second example is subspace embedding. This is a tool that people use for computational linear algebra. So the idea now is that we've got an r-dimensional subspace in a high-dimensional space. Here you can see this plane here, which is a two-dimensional flat in this high-dimensional space. And we'd like to somehow preserve the geometry of that plane after embedding the large dimensional space into a lower dimensional space. Of course, the embedding dimension needs to be at least the dimension of the plane that you're trying to preserve. So the goal is to approximate an r-dimensional subspace in a high-dimensional space after embedding it into a constant times r dimension, say 2r or 4r or something like that. So how could we accomplish this goal? Well, we could stare at the data very hard and try and find some patterns, but there's an easier mechanism, which is just to apply a random matrix to these vectors to reduce their dimension. This is called randomized linear dimension reduction. It succeeds with high probability for both of these problems with appropriate constructions of the random matrix. And the basic example, which you should have in mind, is a Gaussian matrix phi, where each of the entries is mean 0 and has a variance which is just designed to ensure that the vectors stay on the same scale after you've embedded them. Okay. And this example dates back to a paper of Indik and Motwani in 1998, which was a re-envisioning of the work of Johnson and Lindenstrauss, which was based on a random partial isometry. Okay, so Gaussian matrices can be used to take the dimension of data from a high dimension to a low embedding dimension while preserving its geometry. Okay, so here's an example of how you might use this idea to solve a computational problem. This is a bit of a fake application, but it is the easiest way to illustrate how these techniques work. So suppose you'd like to solve a least squares problem, minimize ax minus b, Euclidean norm squared, where the matrix A is extremely tall. So there's a massively overdetermined least squares problem. And the sketch and solve method proceeds as follows. It says, these vectors, the columns of this matrix, are too big, so I'd like to reduce them to a lower dimension and work with the reduced data instead. So how do we do that? We draw a random matrix. The embedding dimension should be roughly twice the number of columns of the matrix. You apply that random matrix to the data matrix A and to the right-hand side B, the response variable. And then, given that reduced data, we're going to solve a compressed least squares problem instead, where now instead of being very tall, it's almost square. Okay? So this problem involves much smaller matrices with k rows instead of n rows. And as a consequence, we can solve it a lot faster. And the goal of all of this is to achieve an error bound for the solution to the compressed problem. So we want the residual for the solution to the sketched problem to be comparable with the residual for the original problem, which says that we've almost solved the problem. Okay? And this can be effective when the residual here is extremely small. So if the right-hand side B is almost in the range of A, then the optimal residual is small, and therefore the computed residual is very small. Okay? So this is an application of sketching, linear dimension reduction, where we reduce the size of the data, we solve a smaller problem, and we get a result which is almost as good as if we had solved the original problem that we cared about. Now, as I said, this is maybe not the most compelling application of randomized dimension reduction. You can also use it to compute low-rank approximations of a large matrix via the randomized SVD, the randomized Nystrom method, or the randomized generalized Nystrom method. I'm not going to talk about these in detail because the algorithms are more complicated, but in the end, they all rely on randomized linear dimension reduction, just as sketch and solve does. Okay. Any questions on this procedure, how this works? I think a lot of people have seen this before. Good. So we're going to be interested in faster methods for dimension reduction, because if you use a Gaussian matrix, things are expensive. So when you develop a sketching method for a linear algebra problem, you need to attend to three things. First of all, you need to construct a dimension reduction map, this phi, which you can apply efficiently, because you don't want to do a lot of work to make the problem smaller. Because if it's expensive to reduce the size of the problem, you might have just solved the original problem to begin with. So that controls the sketching cost. The second thing we need to do is control the embedding dimension. How small did we make these vectors after we compress this? Because that controls the cost of solving the reduced problem, the sketched problem. The smaller the problem, the faster we can solve it. Okay? So we want to control the cost of sketching, the cost of post-processing, and at the same time, that dimension reduction map needs to preserve the geometry of the problem extremely well, or else we're solving some totally other problem. So we need the quality to be good. And these things are in tension with each other. If we don't do any dimension reduction, the quality is perfect, but the post-processing cost is high. Okay, so you see that somehow we're trying to balance all of these desiderata. Now, the Gaussian matrix is a beautiful example, but it's slow. And the reason is that to apply this Gaussian matrix to a vector of length n, it costs order kn arithmetic operations. So for every single vector, we have to do a fair amount of work. On the other hand, we do get very good compression. We can get the embedding dimension to be as small as possible. So if you have an R-dimensional subspace, you can reduce it to 2 R dimensions while preserving its geometry quite well. And that's reflected in this quality statement. So Gaussian dimension reduction does a really good job of preserving geometry. So it's good at compression, it's high quality, but it is extremely expensive in practice. So the idea, which dates back 20 years now, is to use faster dimension reduction methods instead, and hope that we can still achieve good compression of the data and high quality approximations of the geometry. So one example, which we're going to be talking about, is called a sparse stack matrix. I'll define this in detail later. It's a super sparse random matrix. The idea now is that instead of being a dense random matrix like the Gaussian, it's only got zeta non-zero entries per column, where zeta is a tiny number. Okay? So think 4. Okay? So now this matrix is super sparse, and as a consequence, we can multiply it by a vector in zeta times n time, because zeta is 4. This is almost a linear operation on the vector, yeah? Okay, so this is much, much better from the point of view of speed. On the other hand, as Joanna knows, analyzing sparse random matrices is a beast. It's a really challenging problem. And so we have this question about how do we choose the sparsity level? How do we choose the embedding dimension? How do we implement these things so that these dimension reduction maps are efficient in practice? How well do they work? So there are a lot of questions associated with these fast dimension reduction methods, which are sort of resolved in the Gaussian case, but you need these faster methods if you want to develop practical algorithms. Okay, good. So let's do some numerical experiments and see what happens if we use sparse dimension reduction instead of Gaussians. So this experiment takes a matrix of size 50,000 by 50,000 and compresses it so that the number of rows is k, for k equals 500, 2,500, or 25,000. Okay, so we're taking this big square matrix and we're making it into a fat rectangular matrix with not very many rows. And we're going to compare the cost of doing this with a Gaussian dimension reduction map, which is the dashed line, versus a sparse dimension reduction map. Okay, so for the smallest problem, where we're squashing the matrix as much as possible, we see that the cost of doing this with a Gaussian is a few seconds. And for very sparse random matrices, we can get almost an order of magnitude speed up. And so on the horizontal axis, I'm telling you the number of non-zeros per column of the sparse matrix. So you can see that we get an improvement using the sparse matrix, and the sparser the matrix, the more we can improve. Okay. For 2,500 rows, we get a bigger improvement over the Gaussian. For 25,000 rows, we get an even bigger improvement. So the sparse dimension reduction now is 2 orders of magnitude faster. Okay. So you can see that there's a huge difference in the cost of using Gaussian reduction, dimension reduction versus sparse dimension reduction. And again, the sparser the matrix, the faster we can go. Okay, so we'd really like to understand how sparse we can make these matrices and still perform dimension reduction successfully. So this just speaks to the speed. It's unsurprising that applying a sparse matrix is faster than applying a dense matrix. But did we lose anything? So this experiment actually shows what happens if we do matrix approximation using sparse random matrices as compared with dense random matrices. So we've taken 2,300 sparse matrices, and we've made a ranked 200 approximation of each matrix using the randomized SVD algorithm, which is a randomized dimension reduction method. And we've done this both with a Gaussian matrix and with a sparse matrix with 4 non-zeros per column. And what I'm showing you here is the ratio of the error in approximating the matrix using a sparse dimension reduction map as compared with the error using a dense dimension reduction map. Okay, so what you can see here is that the approximation errors are the same regardless of whether we use this expensive dense random matrix or the fast sparse random matrix. So for the most part, the errors are exactly the same. even in the worst case, the sparse dimension reduction map's only 4 times worse. Okay. And there are actually situations where the sparse guy is even better. Okay, so to recap, it's a lot faster to do sparse dimension reduction as compared with dense dimension reduction, and we don't really lose anything in terms of the quality of the matrix approximation. So we should be using sparse dimension reduction. At the same time, from a theoretical perspective, there's a lot we don't understand about it, and this inspires us as computational mathematicians to do some research.
The underlying matrices are sparse themselves.
They're sparse themselves.
Does that matter?
And there's some sense in which the answer is no, it doesn't matter, but it certainly makes both of the algorithms faster, sparse or dense. Yeah. Okay, more questions.
It's harder, right? Because you can worry about catastrophic cancellation.
Yeah, that can happen. All right, good. Shall we move on? All right. So this is all very nice in practice, but how does it work in theory? So on the first slide, when we talked about dimension reduction, I described how we might want to take a subspace in a high dimensional space and map it to a lower dimensional space. And the mechanism for doing this is a standard idea in randomized linear algebra. It's called a subspace embedding. So here's how this works. So suppose we have an r-dimensional subspace in some high dimensional space. So think about a plane. And we have a random matrix that takes the high dimensional space into a lower dimensional space. Now we say that the random matrix is a subspace embedding for that subspace if for every vector in the subspace, the embedding of the vector has about the same norm as the original vector. So we preserve the norms of vectors after embedding up to these swap factors of alpha and beta. And this is true for all of the vectors at the same time with high probability. Okay, so that's a subspace embedding. We're preserving the geometry of the subspace L after reducing its ambient dimension from n to k. Now, it turns out that you can implement lots of linear algebra algorithms using randomized subspace embeddings. So when you have this property, it serves as a black box primitive for proving theorems about algorithms that use these objects, these subspace embeddings. So if you have a subspace embedding, the algorithm is guaranteed to work. And so you can get rigorous error bounds for that sketch and solve for regression, for low rank matrix approximation, and for a variety of other algorithms. So this is the standard technology that people use in randomized linear algebra. And so the challenge then is that you need to prove the subspace embedding property for a particular type of randomized dimension reduction map. So if someone hands you a random matrix that reduces the dimension, you need to make sure that it works for some arbitrary fixed subspace that you don't know. Okay? And so your goal is to make sure that you can embed an r-dimensional subspace into a constant times r dimensions. You would like to preserve the size of vectors up to a constant factor, say 1/2 and 3/2, or 1/2 and 2, or something like that. Okay? And if this is a structured map, you also need to understand how the other parameters, such as the sparsity of the random matrix, enter into the guarantees. Now, a Gaussian is a subspace embedding. This follows in a straightforward way from the rotational invariance of the Gaussian distribution. But as we said, Gaussian matrices are expensive to use. So we'd like to understand when other types of matrices, like sparse random matrices, are subspace embeddings. But actually, it turns out that it's impossible to prove these guarantees sometimes. And as a consequence, we run up against an obstacle, which is that we would like to have a subspace embedding, but there's some mathematical obstruction which prevents it from happening. And so if at first you don't succeed, you should lower your standards. Yeah.
Sorry, you said impossible to prove. Do you mean that
it's actually not true?
Oh, okay.
It's actually not true. Yeah,
Yeah.
unless you use ChatGPT. What?
So statements like was probably 99% always bother me for stupid theoretical reasons. But so, for example, in the Gaussian case, there are well-known large
Right.
deviation
Yep.
methods that say that, well, if it's 99%.
Yeah, I just don't like to quantify the probability because it adds an extra parameter that we need to track.
Okay.
But yes, you can typically get log 1 over delta cost for a delta failure probability
With a Gaussian matrix.
for Gaussian. For other matrices, it might be different. It might be polynomial and delta. Yeah. Okay. All right. Good. So as I said, we're going to lower our standards. So we're going to ask for less. So this is the key definition in this talk. I warned you that this is at least slightly technical. So now we've got an L-dimensional subspace of dimension R in a high dimensional space. And we would like to understand what happens when we apply a random matrix to reduce its dimension from n to k. So we say that the random matrix is a subspace injection for that subspace if it preserves the norms of vectors on average. So this is just a normalization condition. This is pretty easy to get. And if it doesn't make any vector too much smaller. Okay, so for every vector in the subspace, we need to make sure that we don't decrease its size by very much. So in particular, we don't want to send anything in that subspace to 0, because if we send something to 0, it's gone forever. Okay? So we can't do that. And so this just guarantees that we're not sending any vector in the subspace to 0. And as before, we want to embed an R-dimensional subspace into twice R dimensions, say, and we want the injectivity on this parameter to be constant, like 1/2 or something. Okay. So now there are two questions that arise. So this is obviously a easier condition to check than the subspace embedding property because we only have one inequality instead of two. You should think about this as basically being free. And this is just make sure that everything's normalized so that you can't just make the matrix bigger to get this. Okay. So this is a normalization, and this is easier in the other condition because there's one inequality instead of two. So there are two questions. First of all, is this enough to guarantee that your randomized linear algebra algorithms work if you implement them with these subspace injections? And second of all, why does this concept make our lives better? I mean, you can imagine, okay, maybe this is easier, but it turns out that it is fundamentally easier. And we'll come to this in a moment. All right, so any questions on this definition? So we're interested in a random matrix that preserves the geometry of an unknown subspace after embedding it into a much lower dimensional space. But when I say preserves geometry, what I mean is that I don't annihilate any vector in the subspace.
Lower bound seems like the harder one.
Ironically, that is not true. I'll explain.
It shouldn't involve like, does that like any kind of behavior?
Yeah, that's right. That's right. Okay, so here's an example of a theorem you can prove about subspace injection. So consider an overdetermined least squares problem. Let phi be a subspace injection for the range of the matrix A. So we're preserving the range of this matrix, which is an R-dimensional subspace. And if you use this subspace injection in the sketch and solve method, then you are guaranteed that the computed solution has a residual that is comparable with the optimal solution. So the residuals are comparable. And the injection constant appears here in the denominator. So if alpha is 1/2, you get a factor of 2. Okay. Good. So again, there's a tension here. We want the embedding dimension k to be as small as possible so the algorithm's fast, but we also want the injectivity to be close to 1 so that we don't eat an extra factor here. Okay. Now, this is just a sample result, which tells you that the subspace injection property already is enough to guarantee that we can do sketch and solve for overdetermined least squares. But in fact, you can also do low-rank matrix approximation with subspace injections. You don't need this embedding property. That's overkill for all of the basic algorithms here. Okay, great. So in short, injections are enough to do randomized linear algebra, but we still don't know why somehow this is a happier definition than the one we started out with. So, in fact, injectivity is a law of nature. So let me try and explain why this is true. At a very high level, a random matrix absolutely hates having a null space unless it has to. So that's one way of saying this. But here's another way to understand this problem. So assume that the dimension reduction map has IID rows. Okay? So if we apply the dimension reduction map to a vector, the norm is each of the rows applied to the vector, squared, and added up. And because these are identically distributed, each of these random variables is non-negative and has the same distribution. So this is an IID sum of positive random variables. Okay? Good. So if you look at the distribution of a sum of IID positive random variables, it tends to be centered around its expectation, but the distribution is not symmetrical. So it is very likely that the distribution of the sum has a heavy tail, as Dima suggested, because as soon as one of these guys is big, you're out in the tail. Okay? On the other hand, it is extremely unlikely that this sum of positive random variables is small, because as soon as one of them is big, the whole thing is big. Okay? The only way you can be over here is if every one of these images is small. And that's just extremely unlikely to happen because of the independence. Okay? So in short, the norm here, the action of the dimension reduction map on a vector, is big if one of these summands is large, which is quite likely, and that can break your dilation condition, how much it stretches, the dimension reduction map stretches a vector. On the other hand, the norm can be small only if all of the summands are small, which is extremely unlikely, and as a consequence, this dimension reduction map tends to be injective. This is very, very likely. Okay. This is a heuristic reason that the injectivity condition should be true, even if the dilation condition is not. Now, the other reason that this is an appealing change of perspective is that there are lots of tools from high dimensional probability that allow you to control the minimum singular value of a random matrix on a subspace. There's the small ball method due to Polchinski and Mendelssohn. There's a fourth moment theorem due to Oliveira, and there's also a Gaussian comparison technique that I cooked up. And all of these methods give you tools for verifying the injectivity property, okay? Which, as I've said, is much more likely to be true than the dilation property that you also need for an embedding. Yeah.
But so when we do this for all x over some subspace, then of course, the reason we have a subspace, I guess, is because otherwise, in order for the norm to be small, then only one of the directions has to be small.
That's right.
Yeah.
So we are minimizing over the whole subspace.
Mm-hmm.
And so if, for example, the number k is smaller than the dimension of the subspace, there's going to be a vector which escapes from, okay? But that's actually the main reason that the injectivity will fail. So it is not trivial to extend this from one vector to a whole subspace of vectors. And that's why you need these mechanisms from high dimensional probability. But that's not really the subject of this talk, so I'm going to sweep that under the rug. It's just to say that this is the intuition for why this should be true. And unless there's a very good reason, a random matrix is going to be injective.
Okay.
The very good reason being that it doesn't have high enough rank, basically. Okay. Good. So let's talk about what this means for sparse dimension reduction, which was the place that we started. So we were interested in faster methods for dimension reduction for linear algebra, and we argued that the sparse random matrices were very effective for this, but we didn't understand why. Okay, so I mentioned the sparse stack random matrix, so let me detail the construction here just so it's clear what we're talking about. So again, this is a k by n random matrix that maps n dimensions to k dimensions, and we have the parameter zeta, which describes the column sparsity. So here's how you build this matrix. You take a block of B rows, and in each column, you pick one position and then make it plus or minus 1 with equal probabilities. So +1, +1, -1, -1, +1. And you can see that in each of these positions, each column, there's one non-zero in this block. Okay, then we do that again in the next block, we do it again in the next block, and we repeat that zeta times. So because each of these guys has one non-zero, there are a total of zeta non-zeros in each column. Okay, the reason it's called a sparse stack is because we have a bunch of sparse matrices stacked on top of each other. Okay, so it's clear that this is a sparse matrix, and in fact, because of the way we've set it up, if we multiply a vector u into phi, the cost is the sparsity times the number of non-zeros in u arithmetic operations. So this is really cheap, even for dense vectors, and for sparse vectors, it's even cheaper. Now, it should be said that to achieve this in practice, you need a good sparse arithmetic library, which turns out to be harder to come by than you might hope. But that's a software engineering issue, which is outside of my ken. So these matrices are extremely effective in practice, as we've seen. They're a lot faster than Gaussians, and the quality of the low-rank approximations we computed was just as high. But we don't really understand these things. And so there's a challenge as to the theoretical underpinnings for the application of these matrices in computational linear algebra. Okay, so there's a conjecture due to Nelson and Nguyen from 2013 that for any fixed r-dimensional subspace, the sparse stack is a subspace embedding with injectivity 1/2 and dilation 3/2 for some embedding dimension that's proportional to the subspace dimension, and for column sparsity zeta, which is proportional to the log of the subspace dimension. This conjecture is still open, even after 12 years of work, although there are some results that get pretty close now. So the remarkable thing.
Somebody change the numbers a bit low and large. I say change one quarter like the two.
Sorry, what go on?
Yeah.
I don't want to talk about how the conjecture depends on the choice of those numbers.
Oh.
That's not the important part right now. If you put different numbers there, they would appear here and here. And I don't want to, it's complicated enough without an extra parameter. Okay, good. So what you can see from these numerical results is that when the sparsity of each column is 4, that even as the subspace dimension increases, the injectivity tends to be pretty good. And if you take the sparsity to be 8, it basically looks like a Gaussian matrix. And on the other hand, anyway, I don't know about that. Anyway, so the point is that this subspace injection methodology allows you to make some progress on understanding these sparse random matrices. So we can prove that for any r-dimensional subspace, this sparse matrix is a subspace injection with parameter 1/2 when the embedding dimension is proportional to the dimension of the subspace, and when the sparsity is order log r, which is the bottom half of the Nelson-Nguyen conjecture. And this is the important part, because we know that once we have a sparse dimension reduction map, we can implement randomized linear algebra algorithms because they serve as injections.
Joe, it's just a little hard to see the two plots.
Yeah.
What's being plotted on the left and right here?
The left is the injectivity parameter, the right is the dilation parameter. Yeah, I meant to delete the dilation plot because I didn't want to talk about it. But what you can see is that as the subspace dimension increases, the dilation parameters go up. But the injectivity parameters stay constant. And this is for an adversarially chosen subspace.
Yep.
Okay. Anyway, the point here is that we can prove that the sparse random matrix is a subspace injection, but we actually don't know whether it's a subspace embedding or not. And so this, what? It's half the conjecture, but it's the important half. Yeah. Good. So what happens if you use these things to implement linear algebra algorithms? Well, I'm going to talk about two different problems, low rank approximation and, linear regression and low rank approximation. And I'm going to compare the cost of implementing these with a Gaussian dimension reduction map versus a sparse dimension reduction map. And what you see is that as compared with the Gaussian, the sparse dimension reduction map results in an exponential improvement in the cost. And it takes this dimensional factor to a logarithmic factor. And that's true in both of these problems, both linear regression and low rank approximation. So this parameter R becomes log R. So you can see that there's potentially an exponential improvement from using sparse dimension reduction as compared with dense dimension reduction. And these are all provably correct bounds now. Because to check that these results are true, you need this subspace injection technology. And we were able to prove that the sparse dimension reduction map is a subspace injection. Okay. So we've guarantees that sparse dimension reduction for linear algebra is exponentially faster than dense dimension reduction. Okay. Questions on this? Okay. Now, here's a computational example which shows that this stuff actually can be useful in practice. So what we're doing here is simulating a Bose-Einstein condensate using a PDE called the Gross-Pinavsky equation. And here's a picture of what this thing looks like. It's some kind of plasma trapped in a potential field. And then there are places where the wave function collapses. Sorry, not collapse. Where the wave function is 0, and these are the pits here. So there's no probability of finding plasma in those locations. So what we do here is we take this function and we map it into a long vector. It's a two-dimensional function. And then as we simulate this experiment, we get a different column of this matrix for each time step. And so we get, I actually think that this might be the dimensions, and this might be the time steps. But you get a very big matrix, which you think about as the frames in a video, and you'd like to perform proper orthogonal decomposition or an SVD of this matrix to understand what the coherent modes are in this evolving process. And so here's what they look like. 1, 2, 3. And this amounts to the SVD of a matrix with dimension 130,000 by 40,000. This is a fairly big problem. And we want to understand what happens when we do this using sparse dimension reduction as compared with dense dimension reduction. So the first point is that sparse dimension reduction gives the same quality results as dense dimension reduction. So these are two different low rank approximation methods implemented with Gaussians or with sparse matrices. And you can see that the error of all of them is basically the same. So sparse versus dense, same quality. On the other hand, the runtimes are different. So in this picture, this is the ratio of the cost of the sparse dimension reduction, this is the ratio of the cost of dense dimension reduction to sparse dimension reduction. So you can see that the sparse dimension reduction can be up to 10 times faster than dense dimension reduction. And that's in part because we don't have a good sparse library. You'd actually should be seeing 2 or 3 orders of magnitude improvement here. So the point is that we don't lose anything in quality for this computational problem in plasma physics, but we can achieve accelerations between 4 and 12x using sparse dimension reduction. So this is a substantial improvement. And we are guaranteed that the sparse dimension reduction is effective in practice because of this subspace injection theory that we discussed. Okay. Any questions on this? Okay, so I'm going to talk about one more example where this methodology plays a role, and that is for tensor product dimension reduction. So I'm going to be pretty brief about this. So here is the setup. So we're going to be interested in dimension reduction for things that are exponentially large. So we're going to be interested in ambient dimensional space that's d to naught to the L power, or which is huge. And we'd like to reduce these exponentially large vectors to vectors of length k, where you should think about k as being 100 or 1,000 or something like that. So one way that we can do this is using what's called a Cauchy-Rao matrix. And that's a dimension reduction map where each row is a tensor product. So how does that work? We take a base distribution on a low dimensional space. So think about a Gaussian vector. And then we tensor up L independent copies of that Gaussian vector. Okay? So each of these vectors is dimension d naught, but the whole vector has dimension d naught to the L power. Okay? So this is huge. I think there's actually a typo here. Okay. So we have vectors of length d naught to the L, which are formed by multiplying together L vectors of length d naught. And so each of the rows of the dimension reduction map is one of these random tensor products up to a scale factor that depends on the embedding dimension. Okay. So each row is this huge exponentially large vector formed by tensoring up independent vectors, and we do that independently over and over again. So this is very effective for doing dimension reduction on tensor product structured operators. So there are a ton of applications of things like this. So as you may imagine, it's extremely useful for problems in quantum chemistry and quantum information science, because these naturally lead to tensor product structured operators, which are exponentially large. Okay. So there's a lot of exciting recent research on this kind of tensor dimension reduction, but it's simply not well understood yet. And there are two questions we can ask. One is, how do we analyze, design linear algebra algorithms using tensor dimension reduction? And do they work? Can we prove theorems about their accuracy, the cost of these algorithms? And the answer now is yes, because of the subspace injection technology. So we have a theorem which states that these tensor product dimension reduction maps are in fact subspace injections. So if you take each of these short vectors to be a random vector that's uniform on the sphere, and you tensor together L times, then for any R-dimensional subspace in the large space, this map phi is a subspace injection with constant injectivity. So that means we only have the size of a vector, provided that the embedding dimension is proportional to the subspace dimension times the fact that it's exponentially large in the subspace at the number of tensor factors. Okay. So this is a very big prefactor here. But on the other hand, if the base dimension d is like 1,000, this is an exponential improvement over 1,000 to the L. Okay. The second claim is that if we want the embedding dimension for this R-dimensional subspace to be like 2R or 4R or something like that, we can achieve that goal, but now the injectivity is exponentially small on the tensor order L. So if we tensor together 10 things, you should expect this to be like 2 to the minus 10 or something. So 1 part in 1,000. Okay. So what we're seeing here is that we do see exponential behavior depending on the order of the tensor somewhere, either in the embedding dimension or in the injectivity. You're stuck with one of these phenomena. You can't get rid of it. So this is not an artifact of the proof technique. This is a real phenomenon that happens in the world. Nevertheless, what we have shown here is that we can do dimension reduction for subspaces and very high dimensional spaces by applying these tensor structured dimension reduction maps because they are subspace injections. And as we saw before, we know that if we implement linear algebra algorithms with subspace injections, we get guarantees on their performance. So now we know that we can implement those same algorithms using tensor product dimension reduction. Okay. Now, briefly, do we expect these things to be subspace embeddings? The answer is not really. And the reason is that the dilation factor grows like log of the subspace dimension to the L power. This is, again, the heavy tails that you're talking about, Dima. So these things simply aren't embeddings. Okay. But they are injections. Yeah.
Can you reform your assumption to be sampled like a sparse vector?
I don't know what happens with sparse vectors. Yeah.
So, or any kind of random matrices, if the scale behavior is sort of asymmetric, like one side is scale, the other side is not, then we should expect this value. That's right. Because I'm just assuming that I'm just taking the subspace injection property to be one, the lower side of the embedding thing.
That's right.
And usually for Gaussian and everything, you can just take the
Yeah.
expectation of that thing, so it is equal to the normal detector. Then you show, in the case of Gaussian, it's just a symmetric concentration.
Yes.
In this case, it's clearly not. So
It's not. That's right.
So anytime if you have a random matrix, there is this asymmetry.
I hesitate to make a general proclamation, but what you will see is that if the rows of the random matrix have heavy tails, then you do expect that the random matrix itself will inherit that heavy tail in the dilation parameter. Yeah. Okay. All right. So here's a short example of how this applies to a computational problem in quantum chemistry. This is kind of a toy problem, but it gives you some sense about what to achieve. So we're interested in a matrix of dimension 2 to the L by 2 to the L, which is the Hamiltonian of the transverse field Ising model. This is a spin chain. So each of the spins has a two-dimensional state space, and you're tensoring together L of these guys. And the Hamiltonian is an operator on that 2 to the L dimensional space. And what you need to compute is the trace of e to the minus beta times this exponentially large matrix. It's called the partition function of the model. And this is one of the basic quantities that arises in the physical setting. So we can perform this dimension reduction on this tensor structured object using a Patry-Rao, a tensor product structured dimension reduction map that takes us 2 to the L dimensional space. I think this should be one copy of this, not two, down to k dimensions. And we're, for concreteness, taking the chain of 16 spins. So the space is 2 to the 16. So 64,000 dimensions. Okay, so we're going to compare a few different algorithms for this. One is the simplest trace estimator, which is dimension reduction applied quadratically. It's called the Girard-Hutchinson trace estimator. And this is complete garbage. It provides no information about the partition function. But you can implement fancier kinds of trace estimators using low-rank approximation. Low-rank approximation is guaranteed to work by the subspace injection property. And as a consequence, we can develop much more reliable algorithms for computing this trace as compared with the simplest thing. And these are all justified using the subspace injection theory. And what you can see is that using these more sophisticated estimators, based on tensor product dimension reduction, justified by the subspace injection theory, you can get 6 orders of magnitude improvement over the baseline. Here 10 orders of magnitude, here 12 orders. Okay, so all of these algorithms are implemented using these highly structured dimension reduction maps, and the analysis of these maps goes through the subspace injection property, which guarantees end-to-end that these algorithms are effective in practice, which is borne out in this numerical experiment. And you cannot get the same kinds of guarantees if you require this embedding property. The injection property is necessary to get the analysis correct. Okay, so I realize that this experiment is pretty hard to understand if you don't have some familiarity with quantum chemistry. What I want you to take away from this is that using structured dimension reduction maps for randomized linear algebra allows for substantial gains in terms of the speed of the algorithms without any loss in performance. And this concept of a subspace injection allows you to analyze linear algebra algorithms and guarantee that they work. And it gives you a mechanism for proving that the dimension reduction maps meet the requirements to implement those algorithms. And there are a range of applications in modern scientific computing and related areas that benefit from this work. Okay, there are a bunch of papers, and that's it for me. Thank you.
Might have missed this, Joel. What's the
Yeah.
embedding dimension you used in the Cauchy-Rao?
Oh, it's the horizontal axis.
Oh,
So
okay.
K is the number of math-x.
Yeah. So the theory says 3 to the 16.
Yeah, but we don't actually see that.
Oh.
Well, it says two different things. One is that it could be 32, and which is
a lot closer to
right
32
here,
than
a lot closer to 32. And so we're not actually paying for that bad injectivity parameter. Yeah. Yeah.
Okay, great. So thanks, Joe, for the great talk. So now we'll welcome questions. Please ask.
Yeah. Zhao Wang.
So for linear least square, so do you have an estimate about the distance between the least squares?
No, you have to pay for the conditioning of the matrix, just like usual, right? So it's easy to get bounds on the residual, but it's hard to get bounds on the.
Why small say 0?
If it's if
you can consider subset
Right.
of equations.
right, so you do this the way you usually do. You get a bound for the residual, and then you pay for the conditioning if you want to get a comparison of the computed solutions, just like always.
But I'm curious about, but if the residual is not very small, say let's say 100.
Yeah, then this is garbage.
Then
Yeah.
you compare two sides. That
Yeah,
is-
it's garbage. It's garbage. It's garbage. You should not use sketch and solve for data fitting problems, because for data fitting problems, right, you have a whole bunch of scattered data and the line through it has errors all over the place. The residual's huge. Sketch and solve will give you garbage. It is
Okay.
not good for data fitting.
Okay. This question is efficient if there is a lot of equations and the residue is small. Can I
Yes.
say that?
So this comes up in some applications in optimization of linear algebra. It does not come up in statistics, at least in ordinary regression, where you expect the residual to be quite big. Yeah. Yeah, Dima.
So I was curious, there's an alternative dimension reduction where you form the randomized DFT matrix, which
Yes.
Can you compare?
Yeah, there's an analysis in the paper which tells you that those also are subspace injections when appropriately designed. In practice, they are slower than sparse dimension reduction because DFT libraries are even worse than sparse libraries. But at least theoretically, the performance is similar to what we proved here. Yeah.
And then another question, I'm just curious, so if you look at all these classical results where that you mentioned where you have the approximate isometries gives you good approximation, going from those results to just the one-sided results you have, does that require a fundamentally different arguments, or are they like implicit?
Yeah, the arguments are different. It's all kind of in the same spirit, and I actually don't find this stuff to be enormously interesting. It's just a matter of observing that what happens in this analysis is that the place that people use the embedding is to control things like this. So if the dimension reduction map preserves the size of a vector on average, that is usually enough as a stand-in for the dilation bound. So by Markov's inequality, this is unlikely to be more than 10 times the, right? So that's the simplest way to think about what's happening here, but the proofs actually look somewhat different. Yeah, Arya.
So for BFT, like sample BFT matrices, you actually get better alpha for injection than embedding.
That's hard to say, right? So we didn't actually look at the analysis of the dilation part. We did guarantee that as an injection, they perform similarly with what we proved about the sparse random matrices. But we didn't look at the other case. So I actually am not sure. Yes.
Patients where we would prefer a subspace embedding like hugely over a subspace injection here.
Yeah, there actually are some places where it seems to matter. So in iteratively, what do we call this? Iterative sketch and solve for solving constrained regression problems, it actually does matter that you're controlling the dilation. And those algorithms break if you can't guarantee the condition number of the dimension reduction map on the subspaces, not more than two or something. Yeah, sketch and precondition requires that as well. So there are a range of algorithms where it matters, so far as we understand. But that's not to say that you couldn't design other algorithms that don't care. Yeah, good question. So far, this technology has not addressed all of the problems. It addresses the one which I think of as the most important, which is low-rank matrix approximation. But there are other problems that still outside the scope of this theory. Yeah, Todd.
So this is probably a moot point from an expense point of view, but in country route, if instead of using IID uniform spherical vectors, you sample the whole random matrix from the Haar measure on the symmetric space, would you expect similar results?
Probably even better, but I don't know how you would prove it. Yeah.
But it's basically as expensive as generating a Gaussian matrix. It's probably
Yeah, I mean, part of the benefit of this is that you get dimension reduction maps acting on huge spaces where the constructions are very easy. Because, it's like the cost of this is L times D naught random variables instead of D naught to the L random variables. So there's a huge reduction in how much randomness is going in. And also, the storage and application of this, at least to tensor structured things. Yeah.